Hello, students, and welcome to this new chapter, Sources of Magnetic Field. In this chapter, we will take a deeper look at the formulas that we are going to use to find the intensity of the magnetic field due to various conductors. So we'll look at the magnetic field due to a straight conductor, a solenoid, a toroid, and a circular coil, amongst other things. Now, in order to do this, we'll be using two important laws. One is the Biot and Savart law, and the other is the Ampere's law, from whose name we get the unit of electric current. So let's go there right now. So let us consider that we have a big conductor that is chopped up into tiny sections. And so right here we're looking at one of the sections of length dl. The length is dl and it's carrying a current I amperes. We want to find out the magnetic field at a distance r meters, and the angle made by the conductor with the line joining it to that point is theta. So there are four factors here: the current, the length of the conductor, the angle, and the distance of that point from the conductor. And according to Biot-Savart law, the total magnetic field is given by mu naught by 4 pi integral I dl by r squared. Now, this is just a unit vector showing the direction of the magnetic field. Therefore, if you want the expression for dB, it is just mu naught by 4 pi I dl by r squared. But when you integrate it, you get the magnetic field due to the entire conductor. So, as you know, mu naught is the permeability of free space, which shows how easily the magnetic field passes through a medium. And for free space, it's 4 pi times 10 to the negative 7 Tesla meter per ampere. I is the current in amperes. dl is the infinitesimal, meaning small length of the conductor. R, again, is the unit vector from dl to the point of interest. And r is the distance between the element and the point. So this is Biot-Savart law. We can apply this law and use calculus to find the total magnetic field due to any shape. And we would be using this to find the magnetic field due to a circular coil later on. So here is an example. Find the magnetic field at the center of a circular loop of radius r carrying current I. Now, I'm going to give you the formula and I'm going to show you how we get this. But it's useful to remember that the magnetic field at the center of a circular loop is given by this formula, where r is the radius of the loop and I is the current. And the direction is perpendicular to the loop given by the right-hand rule. I hope you remember that. So in order to get this formula, we have to first consider a part of that circular loop and apply Biot and Savart's law, and you can see that the angle, the distance, and the current and the length are given here. So we'll be using this. But before we do that, here's another formula for magnetic field due to a small straight segment. So if you have a small segment like this, a straight segment like that, and you want to find the magnetic field r distance away at this point, we're going to use Biot and Savart's law to get that. Okay, but I am not showing you the calculus behind it because that will take a lot of time. You can get it from the textbook. But you're going to end up with, if the conductor is finite, like if it has a particular length, then you are going to end up with this formula, which is very important. And again, theta 1, theta 2 are the angles. So this is theta 1. This is theta 2. I just assumed it to be 45. So it could be anything depending on the length and the distance. So those are the angles. So in this question, the length is given as 0.2 meter. The current is given and R is given. So all you got to do is substitute into this formula and you would get the answer. Now, that's why I had 45 there, because if you look at the numbers, these two, and then you know that if you take the tangent of this angle, you're going to get L by 2 over R. That's the tangent of that angle, and that will give us 45 degrees because it's exactly half. See that? So that will give us 45 degrees because when you divide, you're going to get 1 and tan 45 is 1. I hope that makes sense. Okay. And so when you plug it into this formula and substitute, since the two angles are equal, I just took 2 times that and you get the magnetic field approximately 7.07 times 10 to the minus 6 Tesla. So now the question is, what if the conductor was infinitely long? So if that was the case, then this angle would become bigger and bigger, right? As the length increases, this angle would become bigger, and if of infinite length, then the angle would become 90 degrees on both sides. So for an infinitely long conductor, theta 1 and theta 2 both are 90 degrees, and if you do that, you're going to get sine 90 plus sine 90, which is 1 plus 1, 2. That 2 gets cancelled with the 4 here, and we end up with a formula. B is mu naught I by 2 pi r. So when you work out problems, if it is dealing with an infinitely long conductor, remember to use this formula. So that's exactly what's given here. And again, it's derived using Biot and Savart's law and using calculus, which I'm not sure. Practical applications, you can find the electromagnetic field strength due to power transmission lines, which would be of a greater magnitude. And then understanding how the field of interactions can cause interference in electronic circuits. Predicting how charged particles move near current carrying wires and all that. Okay, so that is what it's useful for. Now, this can be stretched to actually giving us the definition of an ampere. So that's the problem there. But let me go to that situation first. Here is the situation, and go back to those other sections. So what happens if we have 2 parallel current carrying wires and both are infinitely long? Now, as shown in this diagram, one of the conductors, or actually both conductors, are going to be situated in the magnetic field produced by the current due to the other one. Let me explain that. So I1 flowing through, let's call this A, conductor A, will produce a magnetic field as shown at B. That means the conductor B is situated in the magnetic field produced by the current through A. Similarly, A is situated in the magnetic field produced by the current through B. And we know from the previous chapter that when a current carrying conductor is situated in a magnetic field, a force acts on it. We know the formula for the force. It's just the product of the magnetic field, the current, and the length. So in this particular case, there's going to be a force acting on both of these conductors. And it could be attractive or repulsive, depending on the direction of the currents, which we'll have to find out using the right-hand rule. So in this situation, we get a formula simply by look at this. Simply by using B times I times the length. So force is B times I times the length. And B is what? The magnetic field. And we already have the formula for that, right? B is the magnetic field due to that current through the conductor, and that's the formula. So when you have mu naught I, let's say I1 by 2 pi r, then you got to multiply it with I times the length, which is I2 times the length. So that's why we get mu naught I1 by 2 pi r, so that's B, magnetic field, times the current, because we're finding the force due to the second conductor, times the length. Now, the only thing is that the length is brought to the other side. So the force per meter of each conductor is going to be given by this formula, right? For the other one, it's just going to be I2 times I1, which is essentially the same thing. Now, this helps us to define the ampere, because if we make both of these currents 1 and R 1, and of course L is 1 because it's force per meter, then you're going to end up with all of these being 1. It's just mu naught by 2 pi. And what's mu naught? Mu naught is 4 pi times 10 to the negative 7. So that 4 pi and 2 pi cancel out, giving us 2 times 10 to the negative 7. So if 1 ampere current is flowing through both of those conductors and they are situated 1 meter apart in free space or vacuum, and then the force on each one of them due to the other would be 2 times 10 to the negative 7 Newton. 2 times 10 to the negative 7 newtons. So 1 ampere is that current which, when flowing through two infinitely long conductors, parallel conductors, creates a force of 2 times 10 to the negative 7 newtons on each one of them. So that is the basis of defining the ampere. And this is where we use magnetic levitation. So because we see that you have the rails, and on top of that you have the train, and if we could create a repulsive force between them, then we could balance the weight of the train, so much so that it's not actually touching the rails, but it's just floating slightly above it. And the advantage is that there is no friction. It's completely reduced. The only opposing force here we have is the air resistance, which is considerably smaller than the friction between the wheels of the train and the rail if it had been touching. I hope that makes sense. So here's another thing. When currents flow in the same direction, it's going to be attraction. When currents flow in opposite directions, it is repulsion. And then a simple question worked out where you're given the distance, the currents, I say same direction, so it should be attraction. Find the force per meter. Plugging all those numbers, you would get the answer. And then the second part is, what happens if the second wire's current is reversed? Well, then it becomes a repulsive force. Here is a direct question based on this formula where both I and R are given. This is in centimeters, so it has to be changed to meter. Everything else is very simple. Just substitute, you get 1.6 times 10 to the negative 5 Tesla, which is 16 times 10 to the negative 6, or 16 micro Tesla. Okay? All right, here is the definition of the ampere. 1 ampere is the current which, if maintained in two straight parallel conductors of infinite length and negligible cross-section, they have to be really thin for the formula to be applicable, placed 1 meter apart in vacuum or free space, would produce that force between them. Okay. It's a fundamental physical constant. We know that it's one of the base units of the international system of units and the basis for electric standards, and Here is a question which you may look at it simply a substitution of the numbers into the formula. If both wires are carrying 1.5, of course, instead of I1, I2, it becomes 1.5 square. All right. That brings us to the second right-hand rule, which we actually looked at in the previous chapter. So I'm not going to take too much time on that. Remember that, where you hold the conductor in your right hand with the thumb pointing in the direction of the current, and the closed fingers will give you the direction of the magnetic field. Okay. So that is the second right-hand rule, and so that's something we looked at earlier. So now what we're going to do is we will try to apply the Biot-Savart's law to find the magnetic field due to a circular loop at any point on its axis. So this is the loop. The radius of the loop is caps R. It's carrying a current I, so the current is coming in, flowing out through this, and it's Z distance away from the center. So we want to find the magnetic field here. So I'll give you the basic idea without using the calculus. So we have to consider one section of this loop of length dl, and you know that the current is flowing that way there. That's why the arrow. And then to apply Biot and Savart's law, you need those four variables. So theta is shown here. Z is the distance. I is the current. And using the right-hand rule, we know that the magnetic field has to be perpendicular to the plane containing the point and the section. That's why the magnetic field is shown that way. That's using the first right-hand rule. So that section creates a magnetic field along this direction. Now this can be resolved into two components. So you will get, now that's not shown in the diagram, you get the X and the Y components. Now what happens is, when you take a diametrically opposite section, it sets up a magnetic field perpendicular to that plane, which is this one. And now when you resolve that into its X and Y, it's very clear that the Y components are equal and opposite, this being symmetric, so they cancel out, but the X components add up. So once you get the X component, now you can integrate and you can calculate the magnetic field at any point on the axis. When you do that, this is the formula that you get. Please pay attention to all the variables. So now you know caps R is the radius, Z is the distance, I is the current. Those are the three. The angle vanishes. Because if you really look at this angle, it's 3D, so if you hold it correctly and get that line, this is one of the reasons why I needed a video here. If you take this line, you know this angle is going to be 90. It's not as shown in the 2D diagram, it's 3D. And sine 90 is 1. That's why the theta vanishes right at the first step, so you don't see it there, okay? So here is a question. What if you want to find the magnetic field here? Would that be where the magnetic field is maximum? Of course, because the further you go away, it should become less. So here it should be maximum. And to get that, all you got to do is substitute Z as 0, because Z is 0. So when you do that in this formula, if Z is 0, then this whole thing vanishes. And R squared raised to 3 by 2 becomes R cubed. And R cubed cancels with this R squared to give you a caps R in the denominator. That's why we have this formula. This is the magnetic field at the center of the circular loop. Now that is shown here. And there are many applications. You can read that. And there are two simple problems worked out. One for finding the magnetic field at the center. I'm not going to read all the numbers. There's no need. You can just look at that and you should understand. And then that's at the center. This is not at the center. It's a 0.05 meter above the center. So, simple application of Biot and Savart's law. So before we move on, I wanted you to take a look at this diagram. And you see that the magnetic field, due to a circular loop, has this pattern, which resembles the magnetic field due to a bar magnet. Just keep that in mind. Next, let's look at how would the magnetic field be if it was not a complete loop. And what if it's just a current-carrying arc as shown in the diagram? Then, again, the application of the law would give you this formula, mu naught I by 4 pi r phi. In the diagram it was theta, I've changed it to phi. So phi is that angle. So when it becomes a complete loop, phi becomes 2 pi, right? Phi becomes 2 pi, and that's why the 2 pi and the 4 pi cancel out, giving you 2. So it's useful to remember this formula, which is applicable in the case of an arc. So that's been used here to work out two problems where I've given you the angle in each case, and it should be in radians, remember that, and you should be able to use that formula directly to find the magnetic field due to the arc. Okay, that brings us to the second law, a pretty useful law called Ampere's law. And in fact, the application of Ampere's law to find all of those formulas that we did before is much faster and easier. So I'm going to use this to show you how we could get all those formulas that we had to use calculus to get using Biot-Savart's law. But this one makes it so much more easier. There's calculus involved again. Let me explain Ampere's law. So you have a current carrying conductor, and in fact this dot shows that the conductor is placed perpendicular to the screen and the current is coming out of the screen. The current is coming out of the screen. That's why the magnetic field, when you use the second right-hand rule, the magnetic field is counterclockwise. See that? Right, second right-hand rule. So that's why this magnetic field is shown like that, counterclockwise that way, okay? So let's say that you want to find the magnetic field at some point r distance away. So somewhere here, you want to find the magnetic field. So according to this law, to use this law, you have to assume a closed path given by the broken yellow lines, dashed lines. So just assume this path, and that path must be enclosing that current. So your assumed path must have the current in it. And once you do that, we can find the magnetic field B here. Ampere's law states that the closed line integral, you see that closed line integral, because you have line integral, surface integral, and volume integral. In this case, you're integrating over a path, over a line, and it's a closed path, so that's why this symbol, it's a closed line integral of the dot product of B and dl. So B is the magnetic field right there, and dl is the length. So the angle could be anything, right? And you know that when you have a dot product, the angle involved is cosine of the angle, actually. The factor that comes in is the cosine of the angle, because A dot B is AB cosine of the angle. So whenever the angle is 0, you know cosine 0 is 1. And if the angle is 90, then cosine 90 is 0. So keep that in mind. So anyways, on the left side, you have the closed line integral of B dot dl, which according to this law must be mu naught times the current enclosed by the path. Again, mu naught is the permeability of free space. And this law is very useful in cases of high symmetry like cylindrical, planar, or solenoidal. We're going to use that. And it is analogous to Gauss's law for electric fields, which we had used before, right? Okay. So a direct application, use Ampere's law to find the magnetic field at a distance r from a long straight wire. So infinitely long. Remember, we had this formula before, and we can now use this very easily. You know why? Because if you have that conductor, I think I'm drawing it later, but I can do it here. If you have that conductor and you want to find the magnetic field here, r distance away, all you got to do is go B dot dl. And B is going to be constant because you are at the same distance as long as you have, not like I've drawn. If you had it right at the center, the distance of any point would be the same, right? From here. So B is a constant, it's taken out. So you'll have B integral dl. What is integral dl? It is the total length, which would be the circumference, which is 2 pi r. So that's why we get B times 2 pi r is mu naught I. Rearrange and you get B is mu naught I by 2 pi r. Look how simple that is. Okay, so that's how you get that. And here is a question. A long wire has a uniformly distributed current across its cross section. Find B at a radius within the wire. Wow. So this is within the wire. So remember this formula. If it's within the wire, then you get this. But you have to note, if R is 0, that means you're right on the wire. And it's a long, thick wire in this case, see? And if R is right at its center, then it's 0. B is 0. So remember, there is no magnetic field exactly at the center of a long wire. Keep that in mind. Oh, whatever I told you before, that's derived here. So I'm not going to repeat it. That's what you do to get the magnetic field due to a long straight wire. Once again, that the same thing. But remember, it's only applicable, this formula, I mean, to an infinitely long straight wire. And then two problems worked out where you have the distance and the current. And that should be easy. So let's now try to apply it to two more cases to bring it to an end. The second case we're going to apply it is a solenoid. Now, what's a solenoid? A solenoid is an extended coil. So if you have something like a PVC pipe, cylindrical, of course, and you have a cable wound on it with the turns touching each other, but the turns are insulated from each other. So when you look at a solenoid, you might think that, the current, it's actually the coils of turns are touching each other, which they are, but there is a transparent insulation, so the current doesn't flow en bloc. The current has to flow through each turn of the solenoid. That's the purpose. And this flowing current is going to set up a magnetic field at the axis of the solenoid inside. We're going to try to find that magnetic field by using Ampere's law. Now, in order to do that, take a look at this diagram on the left side. So try to understand what this is. So the current flowing through the turns depends on how it's wound. It could either be wound that way or this way. So looking at the diagram, it's very clear that it's wound this way. How do I know? Because at the bottom, the current is coming out, and at the top, it's going in, right? Bottom, it's coming out. Top, it's going in. The X's always show it going in. The tip of the arrow shows it coming out. So that's how it is. So if you now use the right-hand rule, a little reversed, I want you to remember that usually we have the thumb pointing in the direction of the current, and then you get the magnetic field given by the curled fingers. But now what we could do is, if you hold the curled fingers in the direction of the flow of current, which is this way, the thumb will give you the direction of the magnetic field. That's why the green arrows show you the direction of the magnetic field. Now, to find the magnetic field, first we have to imagine the closed loop, which is this one. We are imagining a rectangular loop to make things easy. And we're going to say that part of this loop is inside on the axis, while this part is outside and considerably away, so much so that there's almost no magnetic field here. So there's no magnetic field here, 0. And then these two sections, remember that the angle is going to be 90. And because it's a dot product, cosine of 90 is 0. Hope you remember that. So when you take that dot product here, magnetic field is that way, dl is this way, the angle is 90, cosine 90 is 0, so that also vanishes. So the only part that we need to consider is this part. And if you take this length as x, then it's very simple. Integral b dot dl is mu naught I. So b is a constant at every point here. B is a constant. So b integral d is x now, because that's the total length. Now on the right side, why do we have ni? Because there are n turns in this particular section. N turns in that particular section. And each turn is carrying a current I amperes, is it not? So the total current enclosed is n times I. That's why we have that. Again, each turn carries a current I, and there are n turns, where n can be anything depending on the length you take. And so you get that. And when you rearrange, you get this formula. And because n depends on x, we like to take them as 1. And this is the number of turns divided by the length, which would be the number of turns in 1 meter. Now, this is one of the big mistakes that students make. We're going to replace this with little n. Do remember that little n stands for not the number of turns, not the total number of turns, but the number of turns in 1 meter. So in a problem, you will be given a certain number of turns and the length of the solenoid. You have to either use this formula or divide the number of turns by the length in meters and get this and work it out. Now this is the place where we could find the unit of mu naught, because number is just a number, it has no unit. So it's very clear that this being Tesla, this is Tesla, and this, although it's number, actually I could have made a mistake here. It's number per meter, so that's that meter. So what's going to happen is you're going to get Tesla times meter over ampere. I hope that makes sense. That's the unit of mu naught. And you saw that on page 1 of this lecture, and I kept it so I could explain it here. So all of these units work. So what is Tesla? You can get it from here anyways. So that is the solenoid. Remember, number of turns per unit length. Okay. Applications, electromagnets, MRI, any type of magnetic field generation. Whenever you need a magnetic field, a strong magnetic field, it's always a solenoid that's used. And just remember that the strength of the magnetic field depends on N and I and mu naught. So at this point, let me tell you, you could increase the permeability, because this is the permeability of air. So instead of air, if you had iron in the core of the solenoid, like you had a bundle of iron wires, iron is much more permeable than air. So now the value of mu increases. It becomes mu naught times what's called the relative permeability of iron. And then if you could also have larger number of turns, how could you have a larger number of turns? So there what's done is you have one layer of windings, and over that you have another layer. You have multiple layer of windings over one another. So finally you could get like 3000 turns per meter. Of course, it also depends on the thickness of the cable that you're using. If you have thin cable, you can have more turns in a particular length. It also does depend on I, but there is a limiting factor there too, because if you have a bigger current, then more heat is produced, as we will see later, and then that could break that transparent microscopic insulation between the turns, which would completely burn out the solenoid. So there is a limit to the currents. Anyway, those are the factors on which the magnetic field depends, and we need very strong magnetic fields in MRI and so on. So that's where the solenoids are used. So here is an example worked out. You can see that it's only 1.26 millitesla with that, and only 1000 turns. Okay. Compare B inside and outside. What's the B outside along solenoid? Nothing. Nearly zero due to field line cancellation. So, because you would, first of all, it's further away, and then you have the, you have, well, it's zero because the distance is really big. It's a comparison to the magnetic field on the axis. Compared to the magnetic field inside the solenoid, outside is going to be considerably less, so we take it as zero. Okay. So the final thing where we're going to apply Ampere's law is called a toroid. Now this is a toroid. So as shown in this diagram, you have an iron core over which you have a coil wound, and so you see the winding goes behind this and it comes back up, and that's how it's wound. So it's if you take a coil, if you take a solenoid actually, a flexible one, and then coil it around, you're going to get a toroid. So it's actually a solenoid which you coil around. Okay, and we have to find the magnetic field at the center of the toroid. I want to tell you, do you know what the magnetic field here would be? If you call this the center, that's the geometric center, there would be no magnetic field there. I'll tell you why. Because to find the magnetic field here, you'll have to assume a closed loop containing that that point. What's the current inside this closed loop? Nothing. Now, when I was teaching this one time, a student said, what if you consider this as the section? Then wouldn't there be a current here? And the answer is no. Can somebody tell me why? That is an intelligent question. But still there is no current enclosed. And so you're like, isn't there a current flowing here? Yeah, there is. But the current is flowing, if it's flowing up here, at the back, it's flowing down, canceling out. I hope you understood. So that's why if you take a section here, a loop here or here, either way, there's no current enclosed. So that's no magnetic field here. What about here? To find the magnetic field there, you'll have to consider a section. Is there a magnetic field? Is there a current inside that? No. So third, let's try to find the magnetic field here. And so for that, we consider as a path here. This is the path that we consider. And when you look at it carefully, you understand that the currents don't cancel out. Okay? And then when you apply this Ampere's law, integral dl is once again the circumference of the path. So that means if you take the magnetic field here, the circumference is less, right, of that path. That means the magnetic field is going to be stronger here. And as you go further away, it's going to get weaker. And when you go outside, it's going to become zero. I hope you understood that. Because if it's outside, then you'll have to consider a section here. Look. which means there is no current enclosed because it cancels out. Okay. So it's very simple. This is mu naught times I. Once again, instead of I, you need to have N times I. But this time, N is the total number of turns in the toroid. All right. So that's it. That's why I'm using little n to show that it's the number of turns in 1 meter. But when I use caps N, it's the total number of turns. So here is the formula for magnetic field due to a toroid. Remember, it depends on the radius of that path. If it's smaller, then the magnetic field is higher. Okay, I've already explained that, and if you've been listening, you understand all this. Okay. So there is the formula that we just got, mu naught Ni by 2 pi r, right? And a problem worked out. Check it out. Compare the magnetic field inside and outside. Inside, finite value given by the formula above. Outside, 0 due to no net current enclosed. It's going to be more conceptual questions as we progress because there's a lot of concepts that are tied into these topics. And that's why I am making these videos so students pay attention and focus on what I am focusing on, because that's going to be on the exam. And it's much easier than reading a textbook, which would take hours and hours. So to finish off this chapter, I wanted to talk about 3 kinds of magnetic materials. Not going too deep, there are 3 kinds of magnetic materials, and they are diamagnetic, paramagnetic, and ferromagnetic. Now, diamagnetic materials are weakly repelled by magnetic fields. So that's because when you put a material, a diamagnetic material, in a magnetic field, inside it you have a magnetic field that's opposing the field in which it is kept. Okay. Paramagnetic, they are weakly attracted to magnetic fields. Ferromagnetic, ferro comes from iron, and so that means it's strongly attracted. And here the magnetic domains align even after the field is removed. So that means you take a ferromagnetic material, keep it in a magnetic field, it becomes a magnet, right? Even after you remove that external magnetic field, this material still holds its magnetism. That's why we have permanent magnets. And permanent magnets used to be made of iron, but now we have better materials. There's an alloy called alnico, aluminum, nickel and cobalt, which has more retentivity. That's the term, residual magnetism. So even after the external magnetic field is removed, this material is able to hold a powerful magnetic field inside it. So we have stronger magnetic fields, stronger magnets now. So there's another term called susceptibility. Not going into details, but just know that for diamagnetic, it's negative. Paramagnetic, it's slightly positive. For ferromagnetics, it's highly positive. Now this I've explained, responds to an external field, repelled, weakly attracted, strongly attracted, and retains magnetism. I wanted you to know that, okay? So there are examples given, diamagnetic materials. Bismuth is a diamagnetic material. Magnetic levitation, of course, you need a diamagnetic material because you need repulsion to keep that train suspended or whatever suspended. So how does a material get magnetized? Why can't we magnetize some materials, like wood, for example? It's explained using magnetic domains. So this is how the domain, so I'm trying to say this without going into too many details. Each atom of every element is a tiny magnet. It has magnetism inside it. You know why? Because electrons are rotating around or revolving around the nucleus. And that's a moving charge. Remember that a moving charge generates a magnetic field. That's why each atom creates its own magnetic field. But these atoms are not aligned. That's why they're not a magnet. They cancel out. But when you situate them in an external magnetic field, these turn, if you can look at this, this turns a little bit and aligns more. Look at this. This was exactly opposite, but it's turned, kind of coming towards this. This makes it more clear. This was that way. Now it's towards the magnetic field. This was an arrow which got cut out. Okay. So when you situate these materials in an external magnetic field, the domains move, turn, and get aligned. And so the picture here is that of a paramagnetic material. How do I know? Because these are not completely aligned, you can see. Some of them are slightly twisted, turned. But if this was a ferromagnetic material, all of them would be perfectly lined up. That means it's a stronger magnet. So that's the idea used to explain magnetism. So you can read this. It's once again the same repetition. This is magnetic hysteresis. So when you magnetize something by sending a bigger and bigger current, okay, this is an external magnetic field produced by a current. Now, I'm trying to go too fast, okay. Let me explain. So you have a solenoid and carrying a current, and on the axis of the solenoid, you have some material. Let's say it's iron. And you're sending a current that is increasing in magnitude through the solenoid. As the current increases, the magnetic field on the axis also increases, right? And B is the magnetism that the iron bar that you kept on the axis attains. So you can see that when the external magnetizing field is zero, the magnetic field in the iron is also zero. It starts out zero. Then as you increase the external magnetizing field, the magnetism in the iron increases. And then you start reducing the current, and even after you bring the current to zero, the external magnetizing field here is zero, right? But still there is some residual magnetism. So this much is called retentivity, residual magnetism. So this shows the extent of the permanency of the magnetic field in it. And if you continue reversing the current, because we are on the negative side, so you're reversing the external magnetic field, you'd have to apply a certain magnetic field in the opposite direction to completely demagnetize it. See? You have to apply that much of an opposing magnetic field. That's actually called, what's that called? It's called the coercivity, C-O-E-R-C-I-V-I-T-Y. I know I'm speaking too fast. Can't help it. Otherwise, this would be 3 hours. So you have two definitions here. This is residual magnetism, and this would be coercivity. Okay, and so the process is continued. You keep increasing the magnetic field, and then you keep increasing it back. Reduce it to zero, and increase it again. You get this. So why this is important? That's why I wanted you to know this. You see that this area of the loop shows how much energy is wasted in one complete cycle of magnetization and demagnetization. That means we are looking for smaller areas for electromagnets. Now what happens in an electromagnet is you're sending a current, and when you have a magnetic field, when you turn off the current, you want the magnetic field to go to zero, but it doesn't, unless you have a material which has less retentivity. I hope you're able to follow. And if you want to continuously magnetize and demagnetize this through thousands of cycles, you're trying to save energy. So you're looking for a hysteresis loop that has minimum area, and soft iron has the minimum area. That's why electromagnets are built out of soft iron. There are other reasons. So read this. Hysteresis means the lag between magnetization and the external magnetic field in ferromagnetic material. So, all right, look at this word. Look at this word. You got to go, and saturation of magnetization is the maximum magnetic field that it can have. Okay, so this one, this point A. is the saturation of magnetization. I didn't want you to miss out on that. So that is this chapter in about 50 minutes. And I hope you're really paying attention, but you also have to use the textbook to get the math part, to get the calculus part, so you can thoroughly enjoy these topics. Thank you, and we'll see you on the next one.